Let's look at bagging. We haven't looked at bagging before in this class, but bagging is kind of an intermediate modeling approach or technique in between just a single tree and the random forest. What you do with bagging is short for bootstrap aggregation. It grows multiple trees, but it does it using different bootstrap samples. That is, you'll recall when we created both the training and the test set, the training and the test data set, we split it up into 90 and 10%, and those segments for the data set were fixed. With bagging, what you do is you do that sampling over and over again. So you're constantly sampling a different mix for the training set and the test set, and you're growing new trees out of each one. And if you think about it for a minute, you can see how this would smooth out differences or smooth out extreme perturbations, if I may say that, in the data set. If you just happen to grow an extreme tree that did not, that chose a variable for the initial branch that was such that it made extreme predictions, this would smooth out those differences if you did it over and over again. Now, our part, I believe, and I probably should check, but I think our part, when it grows the tree, it is an exhaustive search of all of the variables. This is a major difference, major point in difference between the recursive tree. What it does is it considers all of the variables and it selects the one that has the most oomph in terms of dividing the leaf nodes into pure sets. So generally speaking, when you use our part, the very first variable that you see split, which is up here, BA is less than 0.335, will be the one that makes the most important distinctive contribution in terms of separating the leaf nodes on either side of that split into unique and separate classifications. Now, there's a price. There's a cost to performing any sort of exhaustive or brute force, if you will, consideration of all of the predictive variables. It's very time consuming. It eats up a lot of resources. In this set, we only have, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We only have 9 predictive variables. So it's not that onerous. But if, let's say you had 20 predictive variables and it has to go through there and consider all 20 of them to find the one that is the most importance, that has the highest importance, you can see how that's going to slow down the processing time quite a bit. However, bagging does have the advantage that it trains the model over and over again on different samples, on different subsets of the original data set. So it's choosing 90% of the original data set to grow each tree over and over again, but it's a different 90%. And therefore, it has some of the advantages of a random forest, or some of the characteristics. You have multiple trees, you have multiple what they call votes. A vote is just simply the prediction that a tree makes. And you can smooth out the rough areas, so to speak. Now, I think in the exercise I asked you to look at the bagging function with, it has an end bag argument, and that's just the number of trees to grow. It also has, you can call this COOB, which means compute out of bag error rate. So when we run this, as you'll see, let's do it. So we use bagging. You have to call up the IPRED library. I'm terrible about skipping steps. You have to have that installed, and then you have to load it. And then we're going to use the bagging function that is in the IPRED library. And it's the same model, type on everything, 100 trees, and compute out-of-bag estimate. What it does is, with each iteration, each tree that is grown on a different 90%, 10% segment of the data set, it tests it trains it on 90 and tests it on 10. Out of bag just simply means the statistics that you're looking at, the numbers you're looking at for error rate, are not based on the original trees that were used in the training. So out of bag error is essentially error that is recorded on a new data set. Now, it's a bit more complicated than that, but that pretty much is the essence of it. So if we run it, and we just did, again, we can look at, if we wanted to, we could look at the object. And it's always good to do this. If you're curious and you use R quite a bit, it's a good idea to start looking at things. And of course, there are 100 trees. See a question there, I'll get right to you. There are 100 trees. All I did was say, show me the structure of this thing. And it spun and spun and spun. Part of that is because it's a list with 100 different records, okay, or components. So, but the point I'm trying to make is that whenever you have a fitted object from any sort of function, any sort of mathematical function or data mining function, it's going to be a very complex object. And when you express it, when you say, well, I just want to see what's in there, I say P2, you don't see nearly anything that's in there. All it reports is what the author told it to report, which in this case is the out-of-bag misclassification error, which is about less than 25%. So you want to get in the habit of examining the fitted object. Now here's a question that says, how does the bagging function know that the original data is split 90 and 10 when we are only referencing the subset data frame? Good. That is a good question. Here, let's look at the function. Hopefully I didn't misspeak. That's always a possibility, but good way to answer that would be to look at the function itself. And we see that formula data, come down here, take a look at data, optional data frame containing the variables, subset, let's look at subset, optional vector specifying a subset of the observations used. To be honest, I can't answer your question off the top of my head. I believe I did read that, though, in the description. If I am mistaken, I apologize, but no, I'm pretty sure. I'm sure it does that. Look, let's hang on. Let's look at a description here. Bagging. See, this is where I got that notion. Simply grows multiple trees, each tree growing on a different bootstrap sample. It then reports the majority vote or mean response across all trees as the prediction. I don't see the link between that and the function call itself, but there is one somehow. Okay, so I don't know. But that's what it does, I believe. Gets you a different bootstrap, a different training set and test set every time.